Hello, welcome back to another episode in the CSC 280 Introduction to Cybersecurity course at Adelphi University. It's been a while since I recorded videos, but we're back at it. Turns out I forgot to record a few over the summer, so here we go. This week's topic is network security. Now, let me start by putting out there that what we're doing in these next couple of videos is high-level stuff, and I will be glancing over some of the technical details in favor of getting the concepts across properly. So while there might be some shortcuts here and there, the essence of what I'm saying, the bigger picture, still holds. I've broken this down into 3 videos. And the first one will explore domain names. In other words, the names of the computers on the internet and what those naming conventions mean from a security perspective. Once we've done that, in the next video, we'll look more in detail at how the internet actually works in terms of moving data along between computers on different networks. And then lastly, we'll look at technologies that are specifically built and designed to increase the security on an enterprise network. Sneak preview: network security is still a very important topic, especially if you are a service provider. If you are mostly a service consumer, it's still good to know about all the network security things, and there are still some basic steps that you need to take. But knowing that many more of our services are now cloud-based and no longer on our own network, and 2, our employees are more likely to be remote or mobile and therefore also not on our own network, the role of network security is diminishing. Even though it's still, for many cases, our first line of defense, it's a thinner line. So we have to keep that in mind as we go through this. So let's start talking about the World Wide Web and DNS, the domain name system. We use web browsers all the time. And even though we typically only type, say, moodle.adelphi.edu in the address bar, that's not the entire address of the website or the web pages that we are trying to load into our browser. The full specification of a page on the internet is shown on this slide here. It is, for example, HTTP, or actually what I should have said was https://moodle.adelphi.edu/courses/view.php ? etc. For us to understand what this means, we'll have to break it down in its core components. So the first part, the HTTP or HTTPS part, is called the protocol, and that's an indication for the language that our computer will speak when it tries to access resources across the internet from this particular computer. HTTP is the Hypertext Transfer Protocol. It's a request-response protocol used to load, amongst things, web pages, images, videos across the internet. We're not going to do a deep dive into the HTTP protocol in this class. We'll do that more in CSC 380, Computer Network Security, and also in CSC 450, Computer Networks. But for now, let's just assume it is a language that computers speak amongst themselves in order to get data transferred from point A to point B, from a remote system to me, the local system. The remote system needs to be identified. I can't connect to a remote system if I don't know where, or at least what, the address of that system is. And in this case, it is called moodle.adelphi.edu. It's just a name. The dots are there for human consumption mostly. Not exclusively, but mostly. Turns out that we're pretty good in breaking things into little pieces and then gluing them back together in order to memorize things. Moodle.adelphi.edu is called the domain name. Just go with that term for now, and we'll figure out what exactly that means in a couple minutes. Then after that slash, after moodle.adelphi.edu, we see /courses/view.php. That is a resource. That is something that is accessible on the remote computer, that we want to retrieve from that computer so we can show it in our browser. Sometimes it's a file, sometimes it's a program. It doesn't really matter to us what it is, as long as we can access it by name. And in order to pass some information into that resource, we can add some parameters. So in this case, we can, for example, say, well, ID equals, 124410. It's just some information passed into the resource, which is located on the computer with domain name moodle.adelphi.edu, which we access using the HTTP protocol. Now, I can leave things out. You'll see that, for example, we'll often see just adelphi.edu. That really means https://adelphi.edu, but it'll work. And that means that only the protocol and the domain name are required in a URL. Everything else is kind of optional. The computer will fill some things in with defaults, other things we just don't need. HTTP or HTTPS URLs are not the only URLs that we deal with. We can, for example, see a mail-to URL as well. It's less common to see it written that way, but it is completely valid to a computer, and again, it works exactly the same way. We have mail-to, which in this case represents the protocol that we're going to be using. In my case, Leune, that is my last name, but that's not relevant. The fact is that it is the mailbox to which email for me is going to get delivered. So it's the name of a mailbox. And then @example.com is the domain name. And again, we can break down this URL in multiple parts. In this case, only the protocol and the domain name are required elements again. Of course, for mail to be delivered, it would be nice to know what mailbox to send it to, so we would have to specify that as well. But what's common between these two, mail-to and HTTP or HTTPS, and there are many others, is that the domain name is almost always there. It is a name for a computer somewhere on a network. It could be our own network, but it could be a remote network as well. And when we really start looking at those names, we can almost think of those as trees, computer science trees, where we have a root node that starts on top, and then we have little branches coming off that root node, and maybe each branch forks in smaller branches until we reach the leaves of the tree, which represents data. So for example, if we have all these host names shown on the slide behind me, google.com, instagram.com, moodle.adelphi.edu, gardencity.k12.ny.us and bbc.co.uk, we can really put them all in one big tree. We start at the root node, and then we start with all the top level domains. So .com, .edu, .us, .uk, etc. Those things that you see at the end of the domain name are called top-level domains, TLDs. And then we can go break down further to see what's in those top-level domains. For example, we can see that .edu is split up into different domains, subdomains of the .edu domain for individual schools. In our case, adelphi.edu. That really just means that we have a branch coming off the .edu domain for Adelphi machines. And we can repeat that again once we get to Adelphi. We can say, okay, one of our leave nodes is called moodle.adelphi.edu, and that is the name of a computer. So we can always think of this as a hierarchy. Now, what is important to note is that in principle, every node in this tree can be managed by a different organization. So if I want to know where .edu lives, I have to go to the root nodes. If I want to know where adelphi.edu is, I have to go to the .edu domain. If I want to know where moodle.adelphi.edu lives, I have to go ask that question at the adelphi.edu node. And that's a process that we call resolution. And specifically, computers are really not good at dealing with names. They want numbers. Think of them as telephone numbers. Except that the telephone numbers for the internet are called IP addresses. IP is short for Internet Protocol. There are two main versions of IP version 6 and IP version 4. 6 is newer than 4. For our discussion though, it's really not that important that there is an IP version 6 and an IP version 4. We're just going to treat them both as exactly the same. Not entirely true, especially from a technical perspective, but it's a shortcut we can easily take. Now, if I say that a computer likes to see a number and not a name, I need to have a mechanism to translate from the name to the number, and maybe even go back as well from the number to the name. And on the internet, that is called the domain name system. It is a massive database, but it's also a database that is distributed. Because remember what I just said, if I want to do something .adelphi.edu, I have to go to adelphi.edu. But if I want to go to ny.us, then I have to go to them. And so each owner of each node in this hierarchy maintains its own area under that node. But that also means that looking data up becomes a little tricky. Let's say that I want to resolve moodle.adelphi.edu. And remember, resolve means to figure out what the IP address is that corresponds to that host name, or that domain name, I should say. Now let's assume that we haven't done this before. Our computer is brand new, as well as is everything connected to the network. We have no memory of anything that has happened in the past. How does that work? Well, it turns out my computer, as I turn it on, will get its network configuration from the network. It's called DHCP. We'll dig more into that in CSC 380, but one of the settings that can be returned to a computer when it powers up is the DNS server that it wants you to use. And so that means that if I want to resolve something, I want to resolve moodle.adelphi.edu to an IP address, I go ask that question of the DNS server. Like, hey, local DNS server, tell me what this is. But the local DNS server is likely going to say, I don't know. But it can find out. It can start looking for the answer. And it does that by going all the way back to the root node of the DNS infrastructure. Of course, you got to start somewhere. And in our case, that's the root nodes, but it also means that those root nodes are hard-coded into your DNS server infrastructure. Now, those don't come dynamically. Those are pre-configured on your local DNS server. So I go to the root of the DNS database and I say, hey, root servers, root name servers, where do I need to go to resolve .edu addresses? And the root name servers will tell me that. They will give me, okay, well, the root DNS servers you can find at that domain name or that IP address. Go ask them if you want to know about something at adelphi.edu. And so we go to that .edu name server and say, dude, I'm looking for moodle.adelphi.edu, but I know your .edu. Tell me where adelphi.edu is. And so the root domain name servers will tell me where to go to resolve host names that end with .adelphi.edu. So at that point I go to the Adelphi name servers, which we control, and I ask the Adelphi name servers, hey, do you know moodle.adelphi.edu? And it says, yeah, I do. That has IP address 192.100.55.209. And that is something that my computer can communicate with. It's just a fancy way of writing down a 32-bit unsigned integer. Now, that's a long process. Remember, I have to go to the root node first, then I get to the edu node, then I have to go to the adelphi.edu node, and then I gotta finally figure out what moodle.adelphi.edu means. That's 4 steps right there. I don't want to have to do these 4 steps each time. So every name server, the thing that resolves those names, will remember what it answered to a specific question for a while. And that means if someone comes back a second time and say, hey, I want to know what moodle.adelphi.edu is, it's first going to look into that cache, that locally remembered answer that it may have sent before. And if it knows what it was, it's not going to do the entire recursion up and down the tree. It's going to just send the answer from its cache. It's not going to remember that forever. DNS has a setting associated with every possible domain name, how long these intermediate name servers are allowed to remember this answer for. Sometimes you might set that for an hour, which means that you only have to go back to do the entire traversal once an hour. Sometimes you might set it for a week, where you can remember it up to a week. Either way, that is how the DNS system works, by traversing the entire tree. Now, we can do translation of name to number. That is called a lookup by a record. But we can also go the other way around. The mechanism is exactly the same, except that we're looking for a different type of record then. We're looking now for a record that maps an IP address to a name. That's called a pointer record. And they don't have to match. The DNS sees that as two different zones, and the zones don't have to be synchronized. It's probably good practice to keep them synchronized, but you don't have to. I can also do other things with DNS. I can use DNS to find name servers. I can use DNS to do all kinds of things. It's a very simple database that works surprisingly well. And I can show you in a demo what it exactly looks like. Now, these A records and these pointer records are not the only records that DNS sends. It can also find out what an email server for a particular domain is. So if I mail me, Leune, at adelphi.edu, my email system provider has to know where to send this email to. Now, what server should I connect to that can do email for adelphi.edu? That's also figured out through DNS. It's a different type of record, but it works exactly the same way. It's called the MX record. MX is short for mail exchange. And so we can do that. The MX record will actually return potentially more than one answer. But it gives priorities. So it might say, listen, if you really need to, use delivery.adelphi.edu. But if delivery does not work for whatever reason, you can use panther.adelphi.edu as well. So we have the ability to specify multiple levels of priority in there so that if one system is offline or breaks, the system has a fallback option to go to. It's very, very useful in that way. Very robust. And I don't have to communicate anything ahead of time. I can do this almost in real time. As people need me, I tell them what they need to know. They can remember it for a while. And when they're done with it, they forget until the next time they need it. DNS does have a couple of issues, more than a few actually. The first thing to keep in mind is that when the DNS server gives me an answer, I am going to trust that answer. Which means that we have a trust issue there again. One of those secure design principles we talked about was minimization of the trust surface. DNS is all about trust. There's no way, in most circumstances, to verify that a DNS system gave me the right answer. There is a system called DNSSEC that uses digital signatures in DNS, but it is not widespread in use. That will help, except, of course, we can then have the next problem. How do we trust the keys used to set those signatures, and how do we update all of that stuff? We talked about that same issue when we talked about the public key infrastructure. So trust is an issue, but it also means that if I am able to lie to a DNS server, one of the intermediate ones, anything that the sub-DNS systems are then going to tell the end users is going to be believed. The other thing is, if I can convince you that I am a DNS server, but I'm actually a malicious DNS server that's going to say, hey, you want to send money to bank.com? Send it to me instead. You're going to trust me. So protecting that DNS infrastructure to make sure that, one, the answers that the DNS server itself receives are correct, and two, that nobody else than you can pretend to be a DNS server is a good step in defending a network. It's all based on trust, and trust fails. The other thing is that if I can convince you of an incorrect answer, in other words, you're looking up bank.com, it should go to 1.2.3.4. Instead, I'm telling you, send it to 10.20.30.40. And you believe me, that means that for subsequent requests, as long as that entry does not time out, you're going to tell everyone about that. And that's called cache poisoning. Until that timer runs out and I have to go re-resolve. But especially during that time to live period, I might be able to serve up incorrect information, which then the clients are going to believe and talk to the wrong computers on the internet. The use of TLS, Transport Layer Security, can help with that, but only to an extent. And lastly, one of the issues that we see is technically not really a DNS issue, it's really more an issue of people, as always, is domain squatting. Let's say that I register adelphi.com instead of adelphi.edu. If someone does not pay attention very closely, they might believe it's actually me. The DNS system does everything it needs to, but because we have names that look the same, we as humans are going to assume that they are the same unless we're paying attention closely. So, not really a DNS issue, but it does relate pretty closely to that. Now, that's bad, but there are also good things. Every user on a system types host names into their browsers, or clicks on links that resolve to host names, or sends email to people, whatever it may be. Almost all network access we do host name based, and all of those host names are resolved at DNS servers. And that means I can have logs at those DNS servers that I can look at and I can analyze for suspicious or unusual activity. It also means that I can go back after the fact when I know that, for example, a computer on my network was compromised. I can go back to my DNS server and say, okay, what domain names did this particular computer try to resolve? And what did they resolve to? Hopefully that gives me more information then. The other thing I can do is, since I control the DNS servers on my own network, I can say, I don't ever want you to go to, say, maliciousdomain.com. And that means I can pre-configure maliciousdomain.com to resolve to an empty page, for example, or a page that says, hey, you just tried to go to a domain that is malicious, don't do that again. Or I can just refuse to answer altogether. That's called DNS sinkholing. And it means that if I know that particular domains are associated with malicious activity, using the DNS system, I can block access to them. Of course, if someone changes their DNS settings, that's not going to be helpful, but at least we have a starting point there. That's the end for this video. The next video will talk a little bit about IP networking and routing.